Today we're diving into something called steam worlds. You might also know them as subneptunes. Turns out they're one of the most common types of planets we're finding out there. Bigger than Earth, smaller than Neptune, and kind of mysterious. So our mission is to explore this new model that's shedding light on these, well, water-rich but super hot planets and what they might be telling us. Okay, let's unpack this. First off, when we talk about subneptunes, your sources are clear, super common, and they seem to have a lot of water.
That's right, incredibly common. But it's really crucial to understand what water-rich means in this context.
Right, not like Earth's oceans.
Exactly, no blue oceans here. These planets tend to orbit very close to their stars, way too hot for liquid water on the surface. Instead, what we think they have are these incredibly thick, dense atmospheres, mostly steam. And below that steam layer, that's where it gets really wild layers of water under immense pressure existing in these exotic phases.
Exotic phases. Okay, that's the part that sounds, well, completely alien. Water that's not gas, not liquid. What does that even mean? What's happening to water under that kind of pressure?
Yeah, it's pretty strange stuff. Here's where it gets really interesting. Under the kind of extreme conditions deep inside these planets, water can become what we call supercritical.
Supercritical.
Uh-huh. It has properties of both a liquid and a gas at the same time. It flows like a gas but dissolves things like a liquid. And then potentially even deeper, you might get superionic ice.
Superionic ice. That sounds like a contradiction.
It kind of is. Imagine the oxygen atoms locked into a solid crystal structure like ice. But the hydrogen atoms, they're zipping around inside that oxygen cage almost like a liquid.
Wow. So solid and liquid simultaneously.
Pretty much. It's a state of matter completely unlike anything we experience day to day. We've actually managed to create these phases for fractions of a second in labs here on Earth. And we think similar conditions exist inside planets like Uranus and Neptune in our own solar system.
Okay, so it's not completely theoretical.
Right. But it's very different from, say, the subsurface ocean on Europa. These sub-Neptunes are much, much bigger, 10 to 100 times Earth's mass, so the pressures and temperatures inside are just astronomical. Understanding that environment has been a huge challenge.
And that challenge, that complexity you're describing, that's where this new model comes in. Developed by researchers at UC Santa Cruz, Artem Agrashin, Natalie Batalla, Jonathan Fortney. It's supposed to give us a clearer picture.
Exactly. What's really innovative about their approach is a couple of things. First, it uses the latest experimental data on how water actually behaves under these intense pressures and temperatures. But crucially, it doesn't just model the planet as it is now, it models its evolution over millions, even billions of years.
Ah, so how it changes over time.
Precisely. Planets aren't static. Their temperature, their internal structure, it all changes. So understanding that history, that evolution, is absolutely vital if we want to correctly interpret the data we're getting from telescopes like, the James Webb Space Telescope.
That makes sense. You need the history to understand the present.
You really do. Especially when you're trying to figure out what an atmosphere is made of based on the light filtering through it.
Okay, dynamic model uses real lab data. But what are the big picture implications? Why focus so much on these steam worlds, which, let's face it, don't sound very habitable in the way we usually mean? How does this connect to finding life?
Well, that's a great question. What's fascinating here is that these planets, even if not habitable themselves, act like giant natural laboratories.
Laboratories.
Yeah, they let us study physics, like how water behaves under conditions we can barely replicate on Earth. Think about superionic ice. Maybe understanding it better could lead to, I don't know, new material science insights down the line. It pushes the boundaries of physics. And perhaps more directly relevant to the life question, understanding these very common planets helps us refine our search.
How so?
Well, if we can confidently characterize these subneptunes, understand their atmospheres and interiors, we can basically say, okay, these probably aren't the places to look for Earth-like surface life.
Right, it helps narrow the field.
Exactly. It saves precious telescope time, allowing us to focus resources on the rarer, potentially more Earth-like candidates, makes the whole search more efficient.
And it circles back to water itself, doesn't it? I saw a quote from Agrashin in the sources saying something like, life can be understood as complexity, and water has a wide range of properties that enable this complexity. He mentions it being an acid and a base, a great solvent, forming hydrogen bonds.
That's a key point. Water is uniquely versatile.
So if water behaves in these truly bizarre ways, supercritical, superionic on these planets, does that hint that maybe complexity, maybe even life, could arise in ways we haven't even conceived of yet, using these exotic water properties?
That's a more philosophical question, perhaps, but it's definitely thought-provoking. I think if we connect this to the bigger picture, this kind of modeling is really fundamental. It helps us trace water, which is everywhere in the universe, through the whole process of planet formation and evolution. Understanding where the water goes and what form it takes is critical for figuring out the conditions on potentially habitable worlds. It shapes the next questions we ask in the search for life.
Okay, these models sound incredibly sophisticated. How will we actually know if they're right? How do you test these predictions about deep interiors and planetary evolution?
Great question. Validation is key. It comes primarily from observations. The James Webb Space Telescope, JWST, is already doing amazing work. It's actually confirmed the presence of steam in the atmospheres of some sub-Neptunes.
So step one confirmed.
Step one confirmed. And it's expected to observe dozens more. Then there are future missions, like the European Space Agency's Plato telescope. Yeah, planetary transits and oscillations of stars. It's specifically designed to find Earth-like planets orbiting Sun-like stars, but it will also gather incredibly precise data on many other planets, including sub-Neptunes. That data, better measurements of planet sizes, masses, maybe even atmospheric composition hints, will be crucial for testing and refining these evolutionary models. Plato will really put them through their paces.
So it's an ongoing process of modeling, observing, refining.
Exactly. Theory and observation working hand in hand.
Okay, so what does this all mean? We've gone from these common but mysterious sub-Neptunes through atmospheres of steam, down into interiors with, frankly, weird water phases. And we have this new way of modeling their entire history. It helps us understand them, but also helps us fine-tune the search for life elsewhere. It leaves you with a kind of provocative thought, doesn't it? If water, just this one molecule H2O, can take on such incredibly diverse and complex forms across the universe, could that mean there are niches for complexity, maybe even life, far beyond what our earthbound experience lets us imagine right now? Definitely makes you think about water's role in, well, everything. Food for thought.